There is a tunnel, and machinery inside that tunnel sends beams of energy in a vast circle.
The Large Hadron Collider, LHC, at CERN, the European Organization for Nuclear Research, has become a focal point of revolutionary scientific discoveries.
The particle accelerator altered the weight of one electron and therefore destroyed our universe and shifted us into the universe that's directly next to it, and therefore things are different in this universe.
This video elucidates 10 compelling reasons why scientists conjecture that CERN has unlocked a portal to an extra dimension, launching us into a new realm of understanding about the cosmos. Number 1. Observation of unexplained phenomena. The Large Hadron Collider, LHC, at CERN is the world's most powerful particle accelerator. At its core, the LHC is a 17-mile ring buried under the France-Switzerland border near Geneva, where subatomic particles zip around at nearly the speed of light. The LHC allows physicists to recreate the conditions that existed a fraction of a second after the Big Bang. During the early operation stages of the LHC, several unexplained phenomena were observed that baffled scientists. For instance, detectors in the LHC started recording an unexpectedly high number of particle collisions at certain energy levels. These anomalous events did not match predictions based on the standard model of particle physics, which has been the cornerstone of our understanding of the subatomic world for the last half-century. Additionally, a series of experiments dubbed as beauty experiments were aimed at measuring the decay of beauty quarks, a type of elementary particle. The results showed discrepancies with the predictions of the standard model, again pointing towards the presence of new physics beyond our current understanding. Anomalies were also observed in the behavior of neutrinos, which are ghostly particles that barely interact with matter. CERN's OPERA, Oscillation Project with Emulsion Tracking Apparatus experiment detected neutrinos seemingly traveling faster than light, contradicting Einstein's theory of relativity. Although later attributed to a technical glitch, such observations sparked widespread debate and excitement about the possibilities they could imply, including the existence of extra dimensions. Moreover, LHC's experiments also produced heavier-than-expected Higgs boson particles. This sparked theories that the excess weight could be the result of interactions with particles or fields in a higher dimension, serving as potential evidence of dimensions beyond our conventional 3 spatial dimensions. Another curious observation pertains to the nature of gravity. Despite being the most familiar force, gravity is the weakest among the fundamental forces of the universe and remains largely unexplained in the realm of particle physics. Some theories suggest that the weakness of gravity can be attributed to its dilution across multiple dimensions, a portion of which could have been accessed by the LHC. While none of these phenomena provide conclusive evidence for the existence of extra dimensions, they have certainly challenged our understanding of fundamental physics. The observations have introduced questions that the standard model cannot answer, thereby pushing the boundaries of science and opening a door towards a possible new dimension. Consequently, scientists believe that these mysteries might just be the gateway to uncovering an entirely new dimension of reality, possibly opened by the behemoth collider at CERN. Number 2. Particle acceleration and extra dimensions. Particle acceleration lies at the heart of the research conducted at CERN. By colliding particles at high energies, scientists aim to unlock the secrets of the universe. In this chapter, we explore how particle acceleration experiments at CERN provide intriguing hints and insights into the existence of extra dimensions. One of the main motivations behind particle acceleration experiments is to probe the fundamental building blocks of matter and their interactions. The high energies achieved at the LHC allow scientists to recreate the extreme conditions that prevailed during the early stages of the universe. It is within these intense collisions that the potential existence of extra dimensions could be revealed. According to certain theoretical frameworks, such as string theory, the universe could possess more than the 3 spatial dimensions we are familiar with. These extra dimensions, if they exist, would be compactified or curled up at scales much smaller than those accessible to current experiments. The LHC's particle collisions, however, could generate enough energy to briefly unfold these dimensions, providing a glimpse into their existence. One intriguing consequence of extra dimensions is the possibility of new particles associated with their existence. These hypothetical particles, often referred to as Kaluza-Klein modes, are predicted to arise from the quantization of the additional spatial dimensions. When particles collide at high energies, the excess energy could be used to generate these elusive particles, leaving behind distinctive signatures in the detectors at CERN. Furthermore, the behavior of known particles could also be affected by the presence of extra dimensions. For instance, in the presence of extra dimensions, particles could move along trajectories that extend into these hidden dimensions. This would lead to missing energy or momentum in the observed collision events, indicating the escape of particles into the extra dimensions. The detection of missing energy or momentum in certain experiments conducted at the LHC has fueled speculation about the existence of extra dimensions. These observations suggest that particles carrying energy or momentum are escaping into unseen dimensions, resulting in an apparent violation of energy and momentum conservation in our three-dimensional world. In addition to missing energy, the study of particle decays can provide valuable insights into the presence of extra dimensions. The decay processes of particles could exhibit deviations from the predictions of the standard model due to interactions with particles or fields in the extra dimensions. By meticulously analyzing the decay products and their properties, scientists can search for anomalous patterns that could indicate the influence of extra dimensions. While no direct evidence for extra dimensions has been observed at CERN thus far, the high-energy collisions and subsequent measurements provide tantalizing hints that cannot be fully explained by the standard model. These intriguing experimental results have led scientists to believe that the exploration of extra dimensions may be within reach. The quest to understand the true nature of our universe continues, driven by the pursuit of particle acceleration and the potential discovery of a portal to another dimension at CERN. Number 3. Quantum entanglement experiments. Quantum entanglement, a phenomenon in which particles become inseparably linked regardless of the distance between them, has long fascinated scientists and has implications for our understanding of the fabric of space and time. In this chapter, we delve into how quantum entanglement experiments conducted at CERN shed light on the possibility of opening a portal to another dimension. At the heart of quantum entanglement is the concept of non-locality, where the state of one particle is instantaneously connected to the state of another, even if they are light years apart. This peculiar behavior challenges our intuitive understanding of causality and implies that information can be transmitted faster than the speed of light. Scientists at CERN have been conducting experiments to explore the boundaries of quantum entanglement and its potential connection to extra dimensions. One avenue of investigation involves entangling particles and then separating them over large distances. By entangling particles in the lab and then transporting them to different locations, researchers can test the limits of entanglement and investigate whether entangled states can extend into additional dimensions beyond our conventional three spatial dimensions. Such experiments provide a window into the behavior of entangled particles and any potential correlations that could exist across different dimensions. Moreover, quantum entanglement experiments at CERN allow scientists to explore the concept of spooky action at a distance, as famously described by Albert Einstein. If extra dimensions exist, they may serve as a conduit for the seemingly instantaneous interaction between entangled particles. By entangling particles and manipulating their properties, researchers can study whether these entangled states transcend our three-dimensional reality and offer a glimpse into the existence of hidden dimensions. While quantum entanglement experiments at CERN have not directly revealed the existence of a portal to another dimension, they offer valuable insights into the fundamental nature of reality and its potential connection to hidden dimensions. The delicate interplay between quantum entanglement and the exploration of extra dimensions pushes the boundaries of our understanding, paving the way for groundbreaking discoveries that could reshape our conception of the universe. As scientists continue to probe the mysteries of quantum entanglement, they remain hopeful that it may hold the key to unlocking the secrets of an elusive dimension beyond our reach. Number 4. Micro-black holes and their implications. The possibility of micro-black holes, tiny versions of their massive counterparts, has intrigued scientists and sparked discussions about their implications for our understanding of the universe. In this chapter, we delve into how the study of micro black holes at CERN provides insights into the existence of extra dimensions and the potential opening of a portal to another dimension. According to certain theories, such as string theory, the existence of extra dimensions could lead to the production of micro black holes at the energies achievable at the LHC. These micro black holes would be incredibly small, with a size on the order of the Planck length, and would evaporate rapidly due to Hawking radiation. The detection of these elusive entities would provide strong evidence for the presence of extra dimensions. The potential creation and detection of micro black holes at the LHC have ignited debates and concerns among scientists and the public alike. Critics have raised questions about the safety of producing such tiny black holes, fearing that they could grow uncontrollably and pose a risk to Earth. However, proponents argue that the Hawking radiation emitted by micro black holes would prevent them from growing significantly, ensuring their safety. By studying the properties and behavior of micro black holes, scientists aim to uncover insights into the nature of gravity and the fabric of space-time. The formation and evaporation of micro black holes would provide a unique laboratory for testing gravity's behavior in the presence of extra dimensions. The decay products and patterns associated with micro black hole evaporation could offer tantalizing clues about the structure of the extra dimensions themselves. Furthermore, the production of micro black holes could also lead to distinctive signatures in the detectors at CERN. The interactions of particles with these tiny black holes would result in characteristic energy and momentum distributions that differ from the predictions of the Standard Model. By carefully analyzing these signatures, scientists can search for deviations that could indicate the presence of extra dimensions and the creation of micro black holes. While the study of micro black holes at CERN remains an active area of research, it is important to note that any conclusive evidence for their existence and their role as gateways to another dimension is yet to be found. The investigation of these elusive entities serves as a testament to the scientific community's dedication to pushing the boundaries of knowledge and unraveling the mysteries that lie beyond our current understanding. As experiments and theories evolve, we inch closer to the possibility of uncovering a portal to another dimension through the study of micro black holes. Number 5. The Higgs boson connection. The discovery of the Higgs boson, a fundamental particle that imparts mass to other particles, was a monumental achievement at CERN. In this chapter, we explore the intriguing connection between the Higgs boson and the existence of extra dimensions, shedding light on the possibility of a portal to another dimension. The Higgs boson was first observed at the LHC in 2012, confirming the existence of the Higgs field and providing a missing piece of the Standard Model of particle physics. This particle plays a crucial role in our understanding of the fundamental forces and particles that make up the universe. However, the Higgs boson's properties and its interactions with other particles also offer clues about the potential presence of extra dimensions. According to some theoretical frameworks, such as models with extra dimensions, the behavior of the Higgs boson can be influenced by interactions with particles or fields in these hidden dimensions. These interactions can modify the properties of the Higgs boson, such as its mass and decay modes, compared to what is predicted by the Standard Model. By carefully studying the properties of the observed Higgs boson, scientists can search for deviations that could indicate the existence of extra dimensions. One possibility is that the Higgs boson's mass is influenced by interactions with particles residing in the extra dimensions. If this is the case, the observed mass of the Higgs boson could serve as indirect evidence for the presence of hidden dimensions beyond our conventional 3 spatial dimensions. By precisely measuring the Higgs boson's mass and comparing it to theoretical predictions, scientists can test the compatibility of different models, shedding light on the potential existence of extra dimensions. The study of the Higgs boson at CERN is not only limited to its direct observations but also extends to its interactions with other particles and fields. By colliding particles at high energies and analyzing the resulting data, scientists can study the Higgs boson's behavior in extreme conditions. These high-energy collisions can create conditions that allow for the exploration of extra dimensions and their potential effects on the Higgs boson's properties. Number 6. Gravity's rainbow and evidence of other dimensions. The study of gravity has been central to our understanding of the universe, and theories about its behavior have played a crucial role in our exploration of other dimensions. In this chapter, we delve into the concept of gravity's rainbow and its implications for providing evidence of other dimensions. Gravity's rainbow is a theoretical framework that seeks to reconcile quantum mechanics with general relativity, the theory of gravity put forth by Albert Einstein. It proposes that the behavior of particles and fields is affected by the energy levels at which they exist. In the context of extra dimensions, gravity's rainbow provides a potential avenue for detecting the influence of other dimensions on the behavior of gravity. According to some models, the existence of extra dimensions can cause the behavior of gravity to deviate from the predictions of general relativity. As particles interact with these hidden dimensions, the energy levels associated with their gravitational interactions can be modified, resulting in a rainbow of energy-dependent gravitational effects. Detecting such energy-dependent behavior of gravity would provide compelling evidence for the presence of other dimensions. One possible manifestation of gravity's rainbow in the context of extra dimensions is the modification of the gravitational force at very short distances. As particles approach the scales associated with the extra dimensions, the behavior of gravity may deviate from the familiar inverse square law. By studying the gravitational interactions between particles at small distances, scientists can search for deviations that could indicate the presence of extra dimensions. Furthermore, the behavior of black holes, objects with gravitational fields so strong that nothing can escape their pull, can also provide insights into the existence of extra dimensions. The presence of extra dimensions can alter the properties of black holes, such as their formation, stability, and evaporation. By studying the behavior of black holes and comparing their properties to theoretical predictions, scientists can test the compatibility of different models and probe the potential presence of other dimensions. Number 7. Role of supersymmetry in the dimensional hypothesis. Supersymmetry, a theoretical framework that proposes a symmetry between fermions and bosons, has been a subject of intense study in particle physics. In this chapter, we explore the role of supersymmetry in the dimensional hypothesis and its implications for the existence of other dimensions. Supersymmetry posits that for every known particle in the Standard Model, there exists a partner particle with different spin properties. These superpartner particles, if they exist, would provide a solution to some of the mysteries and shortcomings of the Standard Model. Importantly, supersymmetry also has implications for the dimensional hypothesis. One of the motivations behind supersymmetry is its ability to stabilize the hierarchy between different energy scales, such as the weak scale and the Planck scale. This stabilization could be achieved through the existence of extra dimensions. In some models, the gravitational effects associated with extra dimensions can counterbalance the quantum corrections to the Higgs boson mass, resulting in a more natural explanation for the observed hierarchy of particle masses. Supersymmetry also provides a connection between particles in the Standard Model and hypothetical particles associated with extra dimensions. The superpartners of the known particles, if they exist, would possess different quantum numbers and properties. Some of these superpartners could be associated with the extra dimensions, providing a link between supersymmetry and the dimensional hypothesis. While the search for supersymmetry and its connection to extra dimensions has been ongoing, no conclusive evidence has been found thus far. The non-observation of superpartners and the absence of experimental confirmation pose challenges to certain models that rely heavily on supersymmetry and extra dimensions. However, the pursuit of supersymmetry continues to be an active area of research, as it offers a compelling framework for addressing some of the outstanding questions in particle physics. Number 8. Energy and momentum conservation violations. The principles of energy and momentum conservation are fundamental in our understanding of the laws governing the universe. In this chapter, we delve into intriguing observations and theoretical considerations that suggest potential violations of energy and momentum conservation at CERN, providing clues to the existence of other dimensions. During high-energy collisions at the LHC, it is expected that the total energy and momentum of the colliding particles are conserved. However, Certain experimental results and theoretical models propose scenarios where energy and momentum conservation may appear to be violated due to interactions with hidden dimensions. One potential explanation for these apparent violations lies in the escape of particles into extra dimensions. According to some theories, during the collision process, particles could momentarily travel into the hidden dimensions, carrying energy and momentum away from our observable three-dimensional space. These escaping particles would leave behind a deficit in energy and momentum, giving the impression of a violation of conservation laws. Experimental observations at CERN have hinted at such energy and momentum imbalances. The detection of missing energy or momentum in collision events, which cannot be accounted for by the known particles in the Standard Model, suggests the possibility of interactions with particles residing in extra dimensions. By carefully analyzing these missing energy and momentum signatures, scientists can investigate the potential influence of hidden dimensions on the conservation laws. While the observations of energy and momentum conservation violations are intriguing, it is important to note that these violations are not definitive evidence for the existence of extra dimensions. Alternative explanations, such as undetected particles or systematic errors, must also be considered and thoroughly investigated. However, the persistence of these anomalies in experimental data and their compatibility with theoretical frameworks encourage further exploration of the dimensional hypothesis. Number 9. String theory predictions and CERN. String theory, a theoretical framework aiming to unify all the fundamental forces of nature, has garnered significant attention in the search for a deeper understanding of the universe. In this chapter, we explore the predictions of string theory and its implications for experiments conducted at CERN. One of the fundamental tenets of string theory is the notion that elementary particles are not point-like entities, but rather tiny, vibrating strings. These strings oscillate in different modes, giving rise to a spectrum of particles with various properties. String theory also posits the existence of extra dimensions, often 6 or 7 in total, which are curled up at scales much smaller than those accessible to current experiments. String theory predicts that the energies reached at CERN's LHC may be within the realm where the effects of extra dimensions become apparent. These extra dimensions can manifest in various ways, such as modifying the behavior of known particles, introducing new particles associated with the extra dimensions, or altering the strength of fundamental forces. By carefully studying the collision data at CERN, scientists can search for signatures that align with the predictions of string theory. One prediction of string theory is the presence of additional particles known as string excitations, or string states. These particles, associated with the vibrations and modes of the fundamental strings, could have distinct properties that differ from those predicted by the Standard Model. By analyzing the collision events and studying the properties of the produced particles, researchers at CERN aim to identify potential string states and probe their connection to the extra dimensions predicted by string theory. While string theory has yet to yield definitive experimental evidence, the predictions it offers provide a rich framework for exploring the nature of the universe. The continued investigation of string theory at CERN and other research institutions contributes to our understanding of the potential existence of extra dimensions and their implications for fundamental physics. Number 10. The influence of the many worlds interpretation. The many worlds interpretation, MWI, is a theoretical framework in quantum mechanics that proposes the existence of parallel universes branching out from every quantum measurement. In this final chapter, we explore the influence of the MWI on our understanding of the dimensional hypothesis and its potential connection to the experiments conducted at CERN. According to the MWI, when a quantum measurement is made, the universe splits into multiple branches, each representing a different outcome of the measurement. This interpretation offers a radical perspective on the nature of reality, suggesting that an infinite number of parallel universes exist, each with a slightly different configuration of particles and forces. These parallel universes could potentially be associated with other dimensions beyond our observable reality. The MWI has significant implications for the dimensional hypothesis. If other dimensions exist, they could be manifested as distinct branches of the multiverse within the MWI framework. Each branch could correspond to a different configuration of extra dimensions. potentially explaining the variations in the fundamental constants and laws of physics observed in our universe. Furthermore, the MWI can shed light on the concept of wave-particle duality and the behavior of particles in the context of extra dimensions. In the MWI, particles are not confined to a specific classical trajectory, but exist as a superposition of different states. These superpositions can extend into extra dimensions, leading to the possibility of particles simultaneously existing in different dimensions, or branching out into parallel universes. While the MWI is a controversial interpretation of quantum mechanics, its influence on the dimensional hypothesis offers a fresh perspective on the nature of our reality. The potential connection between the MWI and extra dimensions opens up new avenues for exploration at CERN, where experiments and observations can provide insights into the existence of hidden dimensions and their manifestation as branches within the multiverse. It is important to note that the MWI is still a subject of ongoing debate and research, and its empirical validation remains a challenge. However, the influence of the MWI on our understanding of the dimensional hypothesis underscores the significance of considering alternative interpretations and their potential implications for experimental investigations.